Hello, in this video we're going to be talking about biconditionals. Bi is a word that kind of means like two and is saying a combination of two different conditionals. So if we take a statement written in if and only if form, this is your big clue that we're going to be using a biconditional instead of the regular if then. Uh, it combines an if-then statement and its converse. So they're only true if the if-then, or like kind of that original statement, and its converse are true. If both directions are true, then we're able to write a biconditional. So for example, here's our if-then. If two planes are parallel, then they never intersect. Yeah, that is true. Then we check its converse. If two planes never intersect, see that swap right there, then they are parallel, doing another swap. If two planes never intersect, they are parallel. That is also true. Since these are both true, we are then able to create this biconditional. If either of these had been false, then we wouldn't be able to write this. If two planes are parallel, if and only if they never intersect. See how we kind of sneak that if and only if, where the then was, get rid of the if at the beginning. Same thing with this one. Two lines are parallel, then they never intersect and lie in the same plane. That's true. Two lines never intersect and lie in the same plane, then they are parallel. True. That allows us to make that biconditional. Again, look at where this then is, and that gets replaced with this if and only if. Let's try doing it ourselves. So we're given a if-then statement, and we're told it's true. So we're just going to assume that this thing is true. We don't have to worry about it's false. Write the converse of each statement. Then we got to determine if that's true. If that's true, then we get to make our cool biconditionals like we did up there. So let's start by writing our converse. So write the converse. We got to take the if. So two numbers multiplied together gives a positive result. Then the two numbers divided also give a positive result. I'm going to get rid of the also when I write the if. So if two numbers divided give a positive result, then the two numbers multiplied gives a positive result. Not quite enough space. Oh gosh, that's crooked. Sorry. So two numbers divided give a positive result. Then the two numbers multiplied gives a positive result. Just a little switcheroo right there. Okay, so is that true? Well, let's think. If two numbers divided give us a positive, so it is something divided by something, that's positive. If we do that same, something times something, does that also have to be positive? Yeah, it does. So this thing is also true. So it could be that they were both negative. We divide them, that's positive. They're both positive, we divide them, that's positive. Either way, a negative and a negative, positive and a positive, that's always going to multiply or divide to be true. Since those were both true, we can now write our biconditional. Our biconditional is just going to swap this then, and instead of that then, we're going to write if and only if. But unfortunately, that means we got to write all that again. Okay, here we go. Two numbers divided give a positive result. I'm going to abbreviate a little bit. Then we put our if and only if. So that is telling us that we have a biconditional here instead of a regular conditional thing. If and only if, the two numbers multiplied gives a positive result. So we checked the first, that was true. They just told us that. We checked the converse, that was also true. We figured that out, and then we were able to write our biconditional. Okay, in this next example, we're trying to write the two conditionals that form the biconditional. So we already have the biconditional, and we want to break it up into the two original statements. So we've got this first part of the statement, a line bisects a segment, and then we've got the second part of the segment, or not the segment, of the statement, after the if and only if. The line intersects the segment at its midpoint. So the first one, I'm just going to use the red one as the first one. So since we want to write the if-then statement, I want to use if and then. So I want to say if a line bisects a segment, then the line intersects the segment at its midpoint. There we go. Okay, if we want to do the converse, all we got to do is swap those around. So the red bit and the purple bit, we're going to swap them around. If and then are going to stay right where they're at. So if, notice how when I swap those around, I swap the uhs and thes because that makes more grammatical sense. Instead of if the line intersects the segment at its midpoint, then a line bisects a segment. It doesn't make as much sense grammatically if the uhs and thes are not in the order that they are. We have to name the line in the segment, and then we can use thes afterwards, just like you wouldn't use pronouns before introducing the person. One place that biconditionals are used quite often is for definitions. Definitions are actually biconditionals. They're just not written exactly like a biconditional. If something can be a biconditional, it makes a good definition. A good definition needs to be precise, use previously defined terms, so you don't want to use the word in the definition. And most importantly for our lesson today is they can be written as a biconditional statement. So these are good examples because they're nice and clear about what's going on, but over here are non-examples. So it's a figure with four right angles. A square is a figure with four right angles, but what about a rectangle? A rectangle's got four right angles, and that's not a square. So that is why this is not a good example. It's not biconditional. Uh, so yeah, that's what I'm writing in the box. So let's try one. So is the following a good definition? Parallel lines do not intersect. That's true. Parallel lines do not intersect, but that's the way we talked about it back in algebra. But in geometry, we learned that no, this is not a good definition because skew lines do not intersect. So an example of a skew line is kind of saying like, hey, this thing doesn't work both ways, where if lines do not intersect, are they parallel? No. So this one is not a good definition. We would need to add on parallel lines do not intersect and are coplanar. That one works in both directions. If lines don't intersect and are coplanar, then they are parallel, and it avoids the skew trouble that we get over there. This is what we wrote in our notes when we had that first definition of parallel lines. If we wanted to write that as a biconditional, we would say two lines are parallel if and only if, where's my if and only if pen? If and only if they do not intersect and are coplanar. That's it for this video. So definitions are a good example of dealing with biconditionals, where you're writing something that works in both directions. Things are coplanar, then they're coplanar and don't intersect. They're parallel. If they're parallel, they do not intersect and are coplanar, and are made up of that combination of original and converse, where both of those statements are true. Thanks for watching. Bye-bye.